Hey, what's up guys, welcome back to Eureka, and today we'll be talking about geometric vectors, which is chapter 1.1 in the level M mechanics book. To begin with, let's define what a vector is. A vector is a quantity that has both a magnitude and a direction. Now, to understand this, let me give you an example. If, for example, you move an object represented by this dot over here 5 meters away from its starting position. This is its starting position. Now, you won't be able to tell if the object is going to be, here or here or here, because they're all 5 meters away, right? Each of them, should be shorter, is 5 meters away from its starting position, meaning that you don't know where the object will be. However, if you specify an angle, let's say this angle from some coordinate axes, okay, this is the coordinate axes, usually x and y. You specify an angle, and that angle is usually with the positive x-axis. It's usually, you can make other angles as well, but that's usually how it's done. If you can specify an angle to that vector, you can differentiate this vector with this one and with that one. So you can tell where the object will be if you specify a magnitude, which in this case is the 5 meters, and the angle, which is theta over here. Okay, so this 5 meters correspond to the magnitude, theta corresponds to the direction. So this means that this vector over here in red that has a magnitude of 5 and a direction of theta is a vector. This red thing that I just drew there is a vector. Now we're going to be describing the angle a little bit later in this section, so in different videos, but that's the general idea. Hopefully I made it clear that the quantity that describes an object's movement is a vector quantity, since it needs a magnitude and direction. Vectors are usually denoted with a letter, for example v, with an arrow on top. Sometimes they can also be denoted by a bold-faced letter, like this bolded v over here. But usually when you write on your copybook, it's going to be that. Bold letters are usually done in textbooks. So now we know what a vector is, how can we actually represent it? Now I actually drew it here, you can see it, this vector, but let's just forget that that thing exists. And let's move on to how we can represent a vector. So we know that it has a magnitude and a direction, and the magnitude can be represented by a length. So this can correspond to a length, and this is an angle. As I said, more on this later, but for now this is just oriented in some direction on the computer screen right now. So let me draw my vector. Magnitude means a length, right? So right now it's just a segment, right? But we need to add an arrow somewhere to specify a direction, because a segment, it doesn't really tell you the direction. It can tell you either in this direction or that. So we need one arrow, sorry, let me draw it again. One arrow that specifies a direction. Therefore, vectors are represented by directed line segments. Let me write that down. Vectors are represented by directed line segments. Now there are two special points that you should know on the vector. One of them is this point right here, and the other one is this. This one is called the tail of the vector, or is called the point of application. This is due to forces can be represented by vectors. I'll explain that later. But forces, for example, you push an object from its corner, it's different from pushing the object from, I don't know, somewhere else. So this point is where you push the object. I'll explain it later as well. This point over here is called the head or the terminal. The terminal point. For this reason, if this point is labeled A and this one is labeled B, vectors can also be represented by writing AB with an arrow on top, or of course the boldface AB. Okay, now that you know what vectors mean and how you can draw them geometrically as an arrow, how can you compare two vectors? Let me rephrase that. When can you say that two vectors are equal? For example, you have this vector v and this vector u, and given that this is, I don't know, 5 meters and this is as well 5 meters. Now we know that vectors are represented by magnitude and direction. Their magnitudes are equal, right? So check. Directions are different because they're pointed in different directions. You can see that. So direction knows. So this means that u and v are not equal. Two vectors are equal if they have the same magnitude, I'll just write with m, and the same direction. Next point. Two vectors are parallel. Two vectors are parallel when their lines of action are parallel. What do lines of action actually mean? It is an imaginary straight line that contains the vector. So the line of action of the vector v, for example, you have this vector v, is this line here. I'll draw it in blue and dotted. So this line, let me draw it better down here, this line. This is the line of action of v. For example, given those two vectors v and u, are they parallel? So obviously they're not. You can see they're not, but like just to prove it, we can draw their lines of actions. So this is a line of action for v. I'll just write LV, I don't know. And then this one is the line of action of u. Clearly those lines are not parallel, so that means the vectors are not parallel. What about those two vectors? This vector v and this vector u. Well, this is not clear anymore because you can see that they kind of look parallel, but they're oriented in different directions, in opposite directions, in fact. However, according to our definition up here, two vectors are parallel when their lines of actions are parallel. It doesn't specify anything with directions. That means let's draw our lines of action. They are sorry for my drawing, they are indeed parallel. So that means those two vectors are parallel. Another thing that you should know before moving on is opposite vectors. So we kind of mentioned it up here a little bit, but for example, you have a vector v and then another vector u, such that they have the same magnitude, opposite directions. then those two vectors are said to be opposite vectors. V and U are opposite vectors. This idea is very important. Let me repeat. Two vectors are opposite if they have the same magnitude, the same length, but pointed in different direction. This vector is pointing this way, this vector u is pointing the other way around. So those two vectors are opposite vectors. Now we can actually generalize what we talked about before. We have opposite vectors over here, and then we have parallel vectors over here. Those are the two examples that I gave. Now, how do we generalize this? I'm just going to write something. I'll explain it later. A vector v can be written as some constant alpha times another vector u. Now, what does this mean? For example, this is your vector v, right? Alpha is called a scalar. This is a scalar. Now, what is a scalar? A scalar is a quantity that can be fully described by a number. This includes, in physical senses, mass and temperature. They don't have a direction, right? You can't say it's 32 degrees outside and it's directed upwards. Like, what does that even mean? You just need a number, right? So that's what a scalar is. But what is a scalar multiple? Because this thing is a scalar multiple of this vector u. What does that mean? You can scale the vector v, into some other vector u. Let me actually just write this opposite way around. Makes more sense like this. Anyways, so that's why it's called a scalar. It sort of stretches this vector v into vector u. It makes it longer. It scales it up. That's what it means. Now, that is when it scales it up when this alpha is greater than 1, right? Or else if it's less than 1, for example, 8 times 0.9 is something that is less than 8, right? For example, that's the length of v, maybe. But 8 times like 1.1 is something greater than 8. So it makes it, in the vector sense, longer, but in the number sense, it makes it bigger. Now, how is this concept down here actually useful to our two concepts up here, the opposites and the parallel vectors? Two vectors are parallel if their lines of actions are parallel, right? Or you can say that two vectors are parallel if they are scalar multiples of each other. That means if this equality holds true, then u is parallel to v. Let me rewrite that, v. Why is that true? Because when you scale a vector up, or anything up, you won't change the direction, right? You're just making it longer or shorter. That means your lines of action will not intersect in one point. Of course, in this case, the lines of actions of v and u, they're the same line, right? So same lines, they intersect at every single point. Two vectors are not parallel when their lines of actions only intersect at one point, like in this case. So a scalar multiple of a vector, this thing over here, it makes a vector longer or shorter. Now, I only talked about the longer or shorter cases. What about when alpha is less than 0, when alpha is negative? Let's try to draw it out. For example, we have this vector v over here, right? And you scale it down to, I don't know, to this vector, and then you scale it down. For example, here is like 0 0.5, 0 0.4, 3, 2, 1. I'll talk about when alpha is equal to 0 later, but when it's, you can see that the length of the vector gradually goes smaller and smaller and smaller, right? It goes smaller. What if alpha is negative? That means the vector v, the new vector, not v, will be flipped around. Sorry, let me just draw it parallel to get parallel. They will be flipped around. So in this case, alpha is something like, I don't know, negative 1.5, because it flips it around and it kind of makes it longer by, I don't know, some 1.5, a factor of 1.5. So we talked about parallel vectors. What about opposite vectors? Well, this is nearly an opposite vector, right? And then we can say that if you have a vector v and another vector u, that means v is equal to negative u, right? Because it just flips it around without changing its length. So that's why the idea of scalar multiples, this is very important. And that's because it can describe two things using just a simple equality. Now, I skipped the case for alpha equal to 0, and I did that for a very good reason. If we actually try to draw this new vector, for example, you have vector v like this, and then you scale it down and down and down till the vector goes like this. It becomes a point. So it's not technically a point, it's still a vector, but the zero vector, that's what we call it, just looks like a point because the tail and the head will come together. They will come together to sort of a point-like thing. We say that the tail and the head are confounded to one point. Now, what does this actually mean? Because when we talk about vectors in the very beginning, we said that it can only be defined by magnitude and direction, right? This zero vector seems to have zero magnitude, and we can't even talk about its direction because it's not pointing anywhere. There's no difference between its tail and its head. They're literally confounded, right? So what conclusions can we make about this? The zero vector, its magnitude is equal to 0. Its direction is undefined. And it's denoted by a 0 with an arrow on top, or a bolded 0, as I said before. Now let's move on to vector addition. To add two vectors, vector v plus vector u, I'll draw this more v-like, there's something called the triangle law. So let me draw any two vectors. This is vector v, for example, and this is vector u. How do we add those two vectors? Now, the triangle law states that you move one of the vectors, it just say u, you move the tail of the vector onto the head of the other vector. That means, let me just redraw everything. This is the v, should be shorter, sorry. This is v, and then this is u. Should be shorter as well. This is u. Right? You simply move the tail to the head of v. This doesn't change any properties about u. It's still a vector. It has the same magnitude, same direction. So, the sum of v and u, v plus u, let's name it, I don't know, w, okay, is this vector over here. From the tail, that isn't with any head, this you can't pick that. From this tail to the head, this is vector w. That's the sum of vector v and vector u. Now, this triangle law can be explained intuitively. For example, you're at point A, and you move to point B. Can be represented by a vector, right? You move some distance in what direction. Now, you move from point B to some other point C, right? So, in total, you move from A to B and B to C, you move from A to C, right? So that's why the triangle law works. It's very intuitive, so it shouldn't need that much explanation. What about subtraction? Remember that subtraction is just addition with a negative sign in front of the second vector. So, this statement, vector v minus vector u, can be written as v plus, well, negative u, right? And what is negative u? We discussed this earlier. Negative u, let me scroll all the way up. The negative of another vector, in this case u, they are opposite vectors. That means, let's go down, the difference between v and u is just v added with the opposite of u. Let's do an example. For example, I want to subtract those two vectors v and I don't know, this vector u. I want to find v minus u. I want to graph it. So what do we do? First of all, this is equal to v plus negative u, right? Let's find negative u. So this is u, right? That means, this implies basically that negative u is this vector. Let me try to draw it. This vector. Same magnitude, different direction. So this is negative u, right? So now we just have a normal addition. We have a vector added to another vector. Let's use the triangle law. So let me redraw everything. This is my v. Now this is my negative u, kind of like this. Triangle law says that you move the tail of one vector to the head of another vector. Let me draw this. This is v. Yeah. Let me draw it better. Yeah, like this. V, and then this is u. Sorry, negative u. And then the sum is just this. From the tail to the head. This right here is v minus u. The following statements that I'm going to write will be stated without proof since it's very intuitive. So, a vector v plus the 0 vector is just equal to the vector itself, right? I think that's really intuitive. Number plus a 0 is just a number. In this case, a vector plus a 0 vector is equal to another vector. Is equal to the same vector, sorry. Now, what about v plus its opposite vector? Well, that's just equal to the 0 vector. It's intuitive as well. If a number subtracted by itself will be 0, in this case, it's a vector added by its opposite vector will be equal to the 0 vector. Next property, we have alpha into negative v, or the opposite vector of v, will be equal to negative alpha all multiplied by v. Now this is very intuitive because, well, alpha times negative v is just times negative 1 times v, right? And then you can, since this is just multiplication, note that we haven't talked about vector multiplication yet, so we'll talk about that later, but for now, we can only multiply scalars with scalars. Those two are all scalars, right? This will be negative alpha, all multiplied by v. It's very intuitive. The last one, however, I will actually give a nice proof about it. So a vector v plus a vector u will be equal to u plus v, right? They are commutative. This is the commutative property of vector addition. Now, obviously this holds true for numbers, so 8 plus 3 equals to 3 plus 8, but we defined vector addition using, where is it? Using the triangle rule, right? So let's do something similar. You have a vector v and a vector u. This is v, this is u. Their sum is just this, v plus u, right? We all know that. What if I move this vector u over here? So it's going to become, let me draw this, something like this, right? We haven't changed anything about this vector, so this is still u, right? We do the same thing with v. Move this here. So it's going to be like this. That is v. We haven't changed its magnitude, we haven't changed its direction, so it's the same vector. Now, triangle rule. u plus v is equal to, well, the tail of one to the head of the other, which is v plus u, right? So we just proved the commutative property of vector addition using this one all together is called the parallelogram law. Anyways, that should wrap up everything for this section. So if you have any questions, please leave it in the comments section below. And as always, easy.